Hello and welcome. So this is the eighth part in our exploration of Lagrange's theorem, and this is part 8 of this exploration. Now we've already talked about what Lagrange's theorem is, right? Given a finite group G, right? If G is finite and H is okay, so if G is finite and we have H some subgroup of G, then it holds that the order of H must divide the order of G. Now we've established this as true, and we not only established it theoretically, but we actually looked at some examples. We looked at particular cosets and realized that particular subgroups of a given group, and realized that, oh, this partition actually makes sense, and indeed the order of every subgroup does divide the order of the group. But still, it's like, if we spend so much time trying to figure out a result, it's worth asking, well, what's it all for? What can we now do with Lagrange's theorem? Sure, we know that the order of every subgroup must divide the order of the group. But why is that such a useful fact? Right? What are the consequences of this result? This is what we're exploring now. Well, what do you think is the value of the fact that for every finite group, the order of every subgroup must divide the order of the group? Well, and there's quite some ideas, right? Maybe this question could be looked at this way instead. Well, okay, fine. Suppose H is actually some subgroup of a group G, all right? And let's say we know that G, right, the order of G, well, the order of G is going to be some natural number. And let's say that we do the prime factorization of the order of G and find that the prime factors of the order of G are, let's say, G is the product of some prime P, Q, R, right? P, Q, R, right? What if the order of G is the prime P times the prime Q times the prime R, right? Where the primes P, Q, and R are not equal to each other. P does not equal to Q, Q does not equal to R. Okay, they're kind of distinct, right? If Q does not equal to R, right? Okay. So maybe this is not the right notation, but the idea is P does not equal to Q, Q does not equal to R does not equal to P. Right? That's kind of what we're saying here. If these are completely distinct, P is distinct from Q, is distinct from R is distinct from P. Okay, if this is the result that we have, well, and we know that H is a subgroup of G, what does that tell us about the order of H? Does this mean that the order of H is either P or Q or R? Let's say we actually get specific numbers. Let's say we find the order of G, and we find that the order of G is actually 2 times 3 times 7. Okay? Maybe times 4. No, okay, let's get another prime. Times 5. Right? And let's say we got some subgroup of H. Right? H is some subgroup of G, sorry. Well, what does that tell us about the order of H? Right? Let's say we did some calculation and found that the order of G, right, the order of H is actually not H, the order of H does not equal to 3. We also did some proving and found that the order of H does not equal to 2, and we found that the order of H does not equal to 5. The fact that that H is a subgroup of G, and the fact that we know that the order of every subgroup must divide the order of the group, right? And we're supposing that, suppose the group had order 2 times 3 times 7 times 5, and we've seen that the order of H does not equal to 3, the order of H does not equal to 2, the order of H does not equal to 5. What does that tell us the order of H has to be? What does the order of H have to be? And given this information, well, what what use does knowing that the order of H divides the order of G give us? Right. Especially if we know the prime factorization of G. If we wrote down G and we found out that G was of the form, let's say, I know, well, it was the product of some primes, right? Let's say its prime factorization was pu p1 mu to the 1. That's the one of the primes dividing 1 and to the power to which it's contained in the cardinality of G, and prime 2 raised to mu to the 2, and prime 3, whatever the prime is, raised to mu to the 3, all the way to the prime j raised to mu to the j. Suppose we knew that the prime factorization of G was actually p1 mu to the 1, p2 mu to the 2, p3 mu to the 3, etc. I guess let this notation not confuse us. What we mean is, for instance, if we had the number, if we had something like, what? Let's say we had 24. Well, 24 could be written as, what? 24 is kind of like 8 times 3, right? That could be written as 2 cubed times 3, isn't it? Okay. Well, in this case, the primes dividing 24 are 2 and 3, and the powers to which they're raised, the maximum power to which each is raised is 2 to the 3, and 3 is raised to the power of 1. And that's kind of what we're saying here is, suppose order of G is p1 to the mu to the 1. That is, we look at all the primes that divide G and we find that there's p1, there's p2, there's p3, there's pj. And we know that the maximum powers to which each prime is raised is mu1, mu to the I, mu to the j respectively. Given this information and the fact that we know that H is a subgroup of G, okay, and we know that order of H divides order of G by Lagrange's theorem, what does that tell us? What does that tell us about, well, the possible orders of H? Does it limit the possible values that the order of H can take? Right. That's one consequence, right, to think about. Well, let's think about another one. Suppose we got some group G, okay? Suppose we got some group G, right? H is we're looking at some subgroup of G and we got some group G, okay? And let's say we found that the order of the group G is just 1 prime. Let's say it turns out to be 7, okay? And let's say we take the order of H and find out that, well, I mean, maybe not the order of H, but let's say we know that H is a subgroup of G, but H is not the identity group. It's not the trivial group, right? It's not the identity group, right? Given Lagrange's theorem that the order of every subgroup must divide the order of the group, what does that tell us the order of H has to be? Does it tell us that the order of H has to be 7? Okay. If the order of H is 7, right? Well, I mean, in this case, maybe we don't even need to go that far, right? This seems to be an extension of what we've been doing before with the different orders. The order that's just a product of elements. 2 times 3 times 7 times 5, x cancels, 3 cancels, and then we get 7. Okay, it's similar to what we've been doing before. So yeah, please do think about this. If we found that the order of a group was 7, okay, then what does Lagrange, and we know that that the subgroup H is not the identity element, right? What does Lagrange's theorem tell us the order of H has to be? And given this information, what use is there? Let's start with that. So could you now deduce or deduce a possible use for Lagrange's theorem? One possible use for it. Okay. All right. So that's one thing. Well, what other possible uses are there of Lagrange's theorem? Let's go back to an example here of order of g equals to 7. Suppose that order of g actually equals to 7. Okay, then, and we know that some subgroup h of g doesn't have order of h does not equal to 1. That is, it's not the identity. It's not the identity group. So it's some group bigger than that. Okay. Well, what if we looked at h and let's say h1 had some elements in it? Let's say we pick some. Is it true that for every h element of big H, uh, well, what's going to be the order of an element of the group H? Okay, let's think about that. What does Lagrange's theorem question? What does Lagrange's theorem have to do with orders of elements of a group? Right. That's a question to think about. For instance, if we have our group G, okay, and we know that the order of G, well, let's see, and we pick some random element G of the group G, okay, little g is in G, all right. Well, I mean, if G is finite, and we're assuming that G is finite, if G is finite, then, well, I mean, order of G is some natural number, right? Well, what about the order of little g? And here the order of an element is being defined as the number of times you can multiply the element by itself. The smallest natural number, m, such that g to the m equals to the identity element. That's what it means here. So what's the relationship between the order of the element, g, and the order of the group, big G? Okay? Given Lagrange's theorem? Well, first of all, first question, is the order of little g, if G is finite, if G is finite, okay, if G is finite, is the order of little g finite as well? Right, this kind of the symbolism for finite. Okay, is that true? Well, let's think about this idea, right? So, I mean, suppose that the order of g was actually infinite, right? Now, what would that mean? That would mean that, well, what would it mean to what would this, well, G0, what would be some element of the group, right? Namely the identity. And then would have G1, right? So, well, and then G2, okay? So, is it possible for, let's say, G2 to be the identity? Or is it possible for G1 to give us the identity, given that the order of G is infinite? Right. How about G2? Is it possible for G2 to give us 1 if the order of G is infinite? Wouldn't saying that G to the power of 2 equals to 1 imply that the order of G actually equals to 2? If the order of G equals to 2, how can the order of G also equal to infinity? So the question becomes raised, well, is it really true if order of G is actually infinite? Right, can G to the power of 2 give us the identity? Well, answer is no. Okay. How about G to the 3? Sorry, not G sub 3, but G to the 3. Can G to the 3 give us the identity? Well, how about by a similar argument as before? Well, if G to the 3 gives us the identity, then it means that, doesn't it mean that order of G equals to 3? If the order of G equals to 3, right, of course, we're also assuming that the order of the elements that came before I mean, none of the elements that came before raised to the power of uh, none of the elements. Okay, so if we are assuming here that the order of G does not equal to 1, order of G does not equal to 2, etc. So the only thing we're taking for granted is now we are evaluating whether the order of G can equal to 3. Well, if the order of G equals to 3, how can the order of G equal to infinity? Right? So can G3 really give us the identity? Right? And how about G4? And so on and so forth. Right? So let's go up to G to the order of big G. Can any of these things give us the identity, given that G is finite? Right? And another question, well, can any of these elements, G to the 0, G to the 1, G to the 2, G to the 3, all the way, and so on and so forth, G to the order of G minus G plus 1. Okay, we've just committed some errors in writing here, so let's not let's take care not to confuse ourselves. Okay, now we have G to the order of G plus 1 and so on and so forth. Okay, we keep going. Well, can any of these elements, can one of these elements be the same as an element that came before? Is a question. Well, how could we rephrase it? Well, suppose that for some I, right, for some I in some natural number I, well, we have G to the I. So the question is, can G to the I equal to G to the J, where J is less than I? Right. So another way to pose this question is, if let's say we looked at G to the 4, if we looked at G to the 4 over here, can G to the 4 equal to something that came before? Maybe can it be equal to G to the 1? Or can G to the, let's say, order of G equal to something that came before? Right, is the question, etc., etc. Okay, and maybe these things that come after, can they equal to something that came before? All right, so yes, how do we resolve this problem? How do we figure out if for some I that came after J, I came after J, that G to the I, can we figure out if G to the I can ever equal to G to the J? Right? And maybe major question is, do we even need to think of it this way? Let's see. Hmm. Okay, maybe an even better way to carry out this expression, because over here we do have some. This might be a way to carry out the exploration, but let's explore differently. So again, before we get lost here, what were we trying to explore? We're trying to explore the following idea: if G if G is an element of a group G, and this group G is finite, so its order is equal to some element, is less than infinity, is sometimes the way it's written. It means that order of G is finite. If G is some element of big G, and order of big G is finite, uh, what we're trying to evaluate is what's the relationship between, what does this tell us about the order of little g, was a question, right? And one thing we're saying is, the question we're asking was, is it possible for the order of big G to be finite, but the order of little g to be infinite? What do you think? So that's part of what we've been worried or thinking about right now. And one thing we notice is that Well, okay. What's the set G? If G is finite, then suppose we set the order of G to equal to some m. Okay, m is some natural number. All right. Well, I mean, is there anything stopping us from writing the group elements like this? G1, G2, all the way up till Gm. Okay. Well, if we can write the group elements like this, G1, G2, G up to Gm, all right, then I mean, in a parallel way, right? So maybe let's make it even more explicit. So now we have G1, we have G2, we have G3 over here, all the way up till Gm. Okay. Now, suppose we picked some element Gi. Let's call it Gi. We pick Gi element of G. That's Gi is one of these G's. Okay. Now we're trying to check whether the order of Gi can be infinite, given that the order of G is finite. Okay. Well, now over here let's write Gi. Right. So now we're considering Gi basically. Well, Gi to the power of 1 is allowed. Gi to the power of 2. Okay. Gi to the power of 3. We continue raising it to different powers until we go to Gi to the power of m. And then, okay. So, one thing, if order of Gi is infinite, okay, could Gi to the power of m give us 1? What does it mean for an element to be an order of let's say, if we say that the order of Gi equals to some r, what does that mean? The definition for that is r is the smallest natural number such that g to the I, g sub I to the r equals to the identity. But if the order of Gi is infinite, okay, what is that telling us? Is it telling us that there is no natural number r such that g sub I raised to the r equals to 1? If that's what it's telling us, if there's no natural number r for which g sub I to the r raised g sub I to the power of r equals to 1, then okay, can any of these values here be 1? For instance, uh, so for instance, g sub I raised to the 1, can that give us 1? Well, suppose g sub I raised to the 1 gave us 1. Well, wouldn't that mean that the order of g sub I is 1? And if the order of g sub I is 1, how can its order be infinity? Okay. How about g sub I to the power of 2? Can the order of g sub I to the power of 2 be 2? Sorry, can g sub I to the power of 2 give us 1? Suppose it gave us 1. Wouldn't that mean that the order of g sub I is infinite? What about g sub I to the 3? Suppose g sub I to the 3 actually gave us 1, the identity. Wouldn't that mean that then the order of g sub I equals to 3? And so on and so forth. So, are we then saying that in the same vein, g sub I to the m plus 1 is not going to give us the identity, g sub I to the m plus 2 is not going to give us the identity, and so on and so forth? Okay? So, now let's notice that when we looked at this collection of objects where we raised g sub I to different powers, these objects here, g sub I to the 1, g sub I to the 2, g sub I to the 3, g sub I to the m, and so on and so forth, we notice that there are more elements of g sub I raised to some power than there are original elements in the group. Okay? Well, is that possible? Does that make any sense? What property of groups does this violate? Okay? So, Another thing to notice is that, well, okay, yeah, let's start with that. So all of these g sub I to the 1, g sub I to the 2, g sub I to the 3, g sub I to the m, all of these elements, well, they are more, if the order of g sub I is really infinity, then there are more elements of g sub I raised to some power than there are elements of the group. Right? But isn't this a problem? Is what we're asking. Isn't this a problem? Because what's one property of a group? Well, a group obviously has many properties. One property of a group is that a group has to be closed. A group is closed under operations. That is, if we multiply any elements of the group, we must get elements of the group back. Okay? Well, okay, g sub I is an element of the group. So is g sub I to the 1, should that be an element of the group? Well, by closure, what does that say? Okay. G sub I is an element of the group. Should g sub I times g sub I, otherwise known as g sub I squared, be an element of the group? Alright. Suppose that's an element of the group. G sub I, g sub I, g sub I cubed. Well, if g sub I is an element of the group, and g is really a group, well, isn't g sub I cubed also an element of the group? And all the way till g sub I to the m, aren't those elements of the group as well? Okay. Well, if g sub I to the 1 and g sub I to the 2 and g sub I to the 3 all the way to g sub I to the m, if all of those are elements of the group, right, then isn't g sub I to the m plus 1 some extra element of the group? If it is an extra element of the group and the group is closed, are we saying that the order of g is at the same time equal to m and the order of g is greater than m? Right? Does that make any sense? Right? Isn't this nonsense? Well, maybe it's not possible to, maybe the only way, it seems, isn't the only way to save ourselves here to think that maybe for some of these other powers, let's say g sub I to the m plus 1, maybe g sub I to the m plus 1 is the same as some element that came before. It's one of the other gi's. Right, so let's evaluate that possibility. Suppose that g sub I times g sub j, right, actually, sorry, suppose that g sub I actually equals to g sub j. Okay, so we're looking at the possibility, what if maybe one of these extra elements that we came up with, right, because if g sub I to the 1 and g sub I to the 2 and g sub I to the 3 all the way to g sub I to the m are all elements of g and all of them are distinct, none of them equals to the one before, doesn't that mean that we have a problem here, that we actually have these elements g sub I to the m plus 1, g sub I to the m plus 2, aren't those extra elements of a group? And if a group has only m elements, how can it have more than m elements is the problem. So doesn't it seem that our issue is that g sub I, that maybe, isn't our issue that maybe some of these elements are actually turning out to be equal to each other? I mean, or let's put it this way. If some of these elements turned out to be equal to each other, maybe it's possible that g sub I to the 1, g sub I to the 2, g sub I to the 3, g sub I to the m, g sub I to the m plus 1, all the way up till infinity. I mean, we never reach infinity, but if it turns out that g sub I, that it's possible for, let's say, g sub I to the k, let's say, to equal to g sub I to the l, where k does not equal to l, if it turns out that this is possible, okay, well, perhaps, doesn't it mean that perhaps it's possible that maybe this collection, right, this collection of sets, this collection of sets gi to the 1, gi to the 2, and so on and so forth, maybe it's possible that all of it, when we consider the elements that are equal to each other, isn't it possible that maybe that gives us the entire group back? Okay? But in particular, suppose we're actually able to prove that okay, let's first step by step. Let's say k does not equal to L. Okay, can G sub I to the k equal to G sub I to the L? K and L are being taken to be natural numbers. Well, if k and L are natural numbers, right, and k does not equal to L, doesn't that mean that one of them must be less than the other? So let's suppose that maybe k is less than L. Okay, we've supposed that k is less than L. So then, isn't it true that if we got this first equation here and multiplied both sides by G sub I to the minus k, right? Otherwise known as G sub I to the k inverse. Well, now we have G sub I to the minus k times G sub I to the k equals to G sub I to the minus k, okay, times G sub I to the L. Alright? So what's G sub I to the minus k times G sub I to the k? Well, that just gives us the identity. Okay, we now have the identity. So now we have, well, G sub I to the L minus k. Okay, right there. Alright, G sub I to the L minus k. Okay, well, if L is a natural number bigger than k, and k is also a natural number, isn't L minus k some other natural number? Well, if it is, then we found some natural number G sub I to the, we found some natural number L minus k, such that G sub I raised to L minus k gives us the identity. But how can this be possible if the order of G sub I is infinite? Remember, we're supposing that the order of G sub I is infinite. If the order of G sub I is infinite, okay, how can there exist some L minus k, some natural number, which when G sub I is raised to that power gives us the identity? Okay. So then, does it seem sensible to say that G sub I to the k can't equal G sub I to the L if k does not equal to L? Okay. So if k does not equal to L, leads us to conclude that G sub I to the k does not equal to G sub I to the L. Okay. Isn't another way of saying that it doesn't it also mean then that none of these G sub I to the 1, G sub I to the 2, G sub I to the 3, G sub I to the m, G sub I to the m plus 1, all of those, isn't that the same as saying that all of them are distinct? If all of these G sub I to the 1, G sub I to the 2, G sub I to the 3, G sub I to the m, and so on and so forth, if all of these G sub I to the some power are distinct, then aren't we saying that the set G sub 1, G sub 1 squared, G sub 1 cubed, G sub 1 to the 4, and so on and so forth, right? All the way till, well, G sub 1 to the order of G, right? G sub 1 to the order of G, well, and so on and so forth, right? Well, okay. If none of these elements in this set, right, let's call it G power if we like, G power, so G power, the let's call it the G sub I power set or something. Okay. Well, it's written badly now, so okay. This set, let's just call it set A. Why make our life harder than it should be? Let's call it set A. Okay. The set A, uh, if none of the elements in this set A, okay, are equal to each other, what does that tell us about the cardinality of A? Does it mean that the cardinality of A is infinite? All right. If the set A has infinitely many elements, right, and each element of the set is an element of the group, because Gi is an element of the group. This was Gi, supposed to be Gi, sorry. Gi. Okay. Well, because G is closed, right, we're saying that every element of A is some element of the group. So gi is an element of the group, gi squared is an element of the group, gi cubed is an element of the group, and so on and so forth. All the elements of A are elements of the group. So the group, so that means there are infinitely many elements of the group, doesn't it? Isn't that what we're saying here? Well, if there are infinitely many elements of the group, and yet we say that the group G is finite, contains only finite many elements, don't we have a contradiction here? Okay. And so the question, again, reposed, if we have some group G, and we have some H that's a subgroup of G, we're supposing that G is finite, okay? Supposing that G is finite, and we have some H that's a subgroup of G, all right? Is it possible for us to find some element little g in big G for which the order of G is actually infinite? Right? Is that possible? Does that make any sense? Right? So in particular, okay, so okay, we know that if G is a group, we know that if G is a group, finite group actually, finite is key. So let's write it like this. If G is a finite group, order is less than infinity, and H is a subgroup of G, okay, then for all G elements of G, well, the order of G can't be infinite. It's not infinite. That is, the order of G is finite, okay? So that means that the order of G is actually some finite natural number k, okay? Let's call it k, and k is some element of the natural numbers. All right. Well, now if this is true, then let's consider the following. G sub 0, G sub 1, G to the 1, sorry, not G sub 0, G to the 0, G to the 2, all the way up till G to the k plus 1, k minus 1, right? Okay. Right. I mean, with no need to continue, is there a need to continue? Because G to the k, wouldn't that just give us the identity? Because if order of G equals to k, doesn't that mean that G to the k equals to the identity? Right. Right. So if G to the k equals the identity, why include G to the k here? Don't we already have it here as G to the 0? Okay. Well, this group here, okay, let's call the group, let's give it a name. Why not? Why not? Why not? Can't leave it unnamed. Can't be that irresponsible. Let's call it B. All right. B is our set. Okay, our set of powers of G, and G is being, since we're saying that, well, if G is finite, then every element has a finite order. So, which means that, well, there exists some k for which order of G equals to k, which is the same as saying that G to the k equals to 1. Okay, so in particular, what this means is that, well, we could create this set B, which has elements G to the 0, G to the 1, G to the 2, all the way to G to the k minus 1. Well, question, is this B a group? Okay. Please verify that B is a group, right? And it's a form of group called a cyclic group, all right? So, cyclic group, and right, if you're familiar with this, great. If you're not, please check out the YouTube videos by Ben Garside. Ben Garside, great explainer. Ben Garside has some YouTube videos. This is Garside. Ben Garside. He has some YouTube videos, especially his YouTube videos on group theory. And there'll be one on cyclic groups, right? So please go there to convince yourself that B is actually a cyclic group. So if B is a cyclic group, well, we also know that B is a subset, right? Isn't B a subset of our group G? Okay. If we have a group that's a subset of, if we have a group B that's a subset of our group G. Isn't that the same as saying that B is a subgroup of G? Right? But what does Lagrange's theorem tell us? Okay. And in particular, does this mean that the order of B must divide the order of G? Okay. Okay. So Lagrange's theorem tells us that the order of every subgroup must divide the order of the group. So if the order of B, the subgroup B, divides the order of the group, all right, and we know the order of B, don't we? What's the order of B? How many elements have we got here? Well, 1, 2, k minus 1 plus an extra one, right? So order of B turns out to be k. Okay. Well, are we saying now that k must divide order of G? Is that a conclusion? If order of B equals to k and order of B divides order of G, doesn't that mean that k divides order of G? Alright, but what was k originally? Well, k was actually the order of any element G in the group. So, are we saying that if G is a group, okay, if G is a group and little g is an element of a big group G, okay, and if G is a finite group, finite, emphasis on finite, okay, is Lagrange's theorem implying, is Lagrange implying that, right, is it implying, right, is Lagrange implying that the order of any element of the group must divide the order of the group, right? Please decide if this is true. Okay, so we've actually run out of time here, so what we're going to do now is, well, obviously we'll stop here. Well, let's think about what we've considered so far. Again, we've been looking at Lagrange's theorem, and the idea has been that the order of every subgroup of a finite group must divide the order of a group. And we said this is all well and good, but what is it good for? And so far we've looked at some ideas. In particular, we've asked ourselves the question, what does Lagrange's theorem tell us about if the order of the group is, let's say, some limited number of prime options, let's say p times q times r, okay? What does that tell us are the possible values for the order of h? Okay, that's the first, that's been one question. Another question we've looked at is, if we have a group G that's finite and we pick some element of the group G, are we saying that the order of G must the order of the element little g of the element must divide the order of the actual group? Is this true if G is a finite group? Okay, and how is Lagrange's theorem connected to all of this? Right. So far that's what we've been doing. So please, and then natural question. Well, are there other consequences? Right? Are there other consequences of Lagrange's theorem? Right. Could you think of other consequences of Lagrange's theorem? What does it lead us to? Right. Otherwise, thank you very much for watching this video and have a relentless week. Bye.